So welcome everyone to today's talk. We have the Honorable Dylan Nelson, who was at Stellenbosch not too long ago.
I'm technically
friend.
still registered as a student, but
So is technically still a student, but you're now a teacher, correct?
no, I'm working as a software developer.
Oh, okay.
Yeah.
So we're very honored to have you back here for a talk that you gave last year as well about voting systems. And the reason that this talk is especially convenient right now is because SUMS, of course, needs a new committee for next year. So I just quickly want to run over this and then I'll hand over to you. The applications are open. They should be, I think, in the chat. I think Ralph put them there. And if you're on the email list, they'll be there and on media and everything. So just be aware if you want to apply to be in the committee next year, be the chairperson, marketing designer, media manager, or event planner. Please don't be scared to apply for it. This year has been a lot of fun, and the talk that Dylan is about to give will decide how we're going to vote if you're in it or not. So with that, I'll hand it over to you, Dylan. Thank you.
Okay, thank you. Let me share my screen, and can I share the whole screen? It's going to be best, and let's can I put this in presentation mode? View. Okay, can you see the whole slide deck? Okay.
Yes.
So we're going to be talking about the mathematics of voting systems, or in particular, actually ranked list voting systems. The idea here is that instead of each person having one vote that they cast for one candidate, each voter ranks all of the candidates in their list of preference. And our goal is to design a system that takes these individual rankings and combines them into a single overall ranking. And so Arrow identified some properties that he thought such a system should have, or that he found other people doing research had considered in the case of individual voting systems, and then proved a general theorem about all such systems, about what properties they, well, turns out can't have. And last time I gave the talk, I gave a lot of sort of philosophical content rather than mathematical content, talking about, what is democracy and how do different countries do it, and is it desirable, and whatever else. That's not going to be my focus today. Today I'm going to be a bit more, it's essentially the same talk, but it's a bit more focused on the actual voting systems and sort of mathematics. And hopefully there'll be time to give a sketch of the proof. But if I can at least give some examples of systems that fails to have the properties that were identified, then that's already well, victory, I guess, is the word. So that's our context. This is an outline of the whole talk. You can play along at home. I've set up a survey on SurveyMonkey. It turns out it has got a feature to let you rank options in order of preference. So you can go to the link on the screen over there, or scan the QR code if you find that easier. It will work on your mobile phone. And then later on, I will use my top secret proprietary voting aggregation method to decide on the overall ranking of the, you'll see in inverted commas, integers that are on the list, and you'll see immediately why it's in quotation marks if you actually follow the link and try to rank these integers. But yeah, so this will at least help you understand what the input is into our system, is a list of preferences from each voter, and you're all voters. So hopefully at least one of you will cast a vote, but I have already, so to test that the system works. So there's at least some data to go by. Okay, so let's first address the clickbait in the advertising for this talk. Some of you may notice this was the poster that was used to advertise this talk. It says, "Is democracy a myth?" This, I complained last year that it's clickbait. I'm going to run the same gag this year. This is clickbait. I think Bettridge's law of headlines might apply. He observed that in his experience, anytime that a headline ends in a question mark, the answer is usually no. And in fact, there was a Twitter account that was dedicated to this premise. It was called @YourTitleSucks. And his tagline is, the answer is no. Unfortunately, it's been inactive since 2015, but here are some examples. Okay, so this is, so the MSNBC had an article asking, is your pumpkin spice shake worth the cost? The answer is no. Can these sensors scientifically prove that UFOs exist? The answer is, of course, no. Does bad grammar stand in the way of true love? Turns out the answer is no, which means that there must be something else wrong with me. And then, is the world heading for its third global financial crisis? I guess hindsight's 2020. So also, last time I gave the talk, it was suggested that I do not use actual political party names because that could be contentious. And I didn't listen, but this time I'll not actually not use any political party names, but I'll include this disclaimer anyway. Political parties referenced in this talk are either the product of my imagination or used in a fictitious manner. Any resemblance to actual political parties, local or abroad, is purely coincidental. I'm not trying to make any political statements with this, although you could argue that is discussing whether democracy works even in principle is a political statement. But I'm just a mathematician. I'm just here to present Arrow's theorem and to try to make it understandable. So as I mentioned, we're going to be talking about, in particular, ranked list voting systems. You don't, the systems require the voters to rank all of the candidates in order of preference instead of picking a single candidate that they like the most. And the goal of the system would be to combine these individual rankings into an overall ranking of all of the candidates. And so we're going to look first and foremost at some properties that we might want such a system to have. And this one is usually not, well, this one is sort of implicitly assumed most of the time. The Wikipedia article does mention it explicitly as the kind of system that we're going to be looking at. The output of our system should only depend on the individual votes actually cast by the voters. In other words, if you have two different elections and everyone votes in exactly the same way, then the outputs should be the same. You're not allowed to pick people at random. You're not allowed to use the weather to decide who is the winner or what the ranking is. It's like an actual, no, you have some kind of algorithm for combining these votes into a single output. It's a pure function, it doesn't depend on external data that's not available. It has to give the same output for the same input every time. And it also identifies what it calls universality, which says that every possible set of rankings that the individual voters provide should actually be accounted for. We can't have a system where we decide not to give an output because someone didn't vote in a way that we like or that we can that we are set up to be able to deal with. And then it would also be nice if every possible outcome is actually obtainable. This isn't strictly necessary because especially when combined with the next property that we're going to desire, this is automatically true. But these two properties are really just saying that our aggregation system should be a function in the mathematical sense, and our nice to have means that it's a surjective function from the space of possible elections to the space of possible rankings of the candidates. So that's the kind of thing we're looking at. And this system should exhibit what is called unanimity. If every single person agrees that candidate A is better than candidate B, the system should also rank candidate A above candidate B. There's no controversy here whatsoever, in my opinion. If everyone prefers A to B, obviously A should be ranked higher than B overall. And most voting systems you can come up with do in fact satisfy this. This is a very trivial thing to satisfy. The one that's a lot more difficult to satisfy and a lot more contentious, and we can have a discussion about whether it's even desirable, but it's the one that Arrow considered, and that's the context in which his theorem exists, is called independence of irrelevant alternatives. So suppose we have two elections, and everyone who preferred the vulture party to the hyena party in the first election still preferred the vulture party to the hyena party in the second election, and vice versa. So as far as these two candidates alone are concerned, the two elections are identical. The other candidates might be re-ranked, but for these two, everyone's preferences are still the same. Then these two should be ranked the same in the output of each election. So if everyone that was ranking the Vulture Party above the Hyena Party still does, and vice versa, and in the first election our system put the Vulture Party above the Hyena Party, it should still do that in the second election. And similarly, if in the first election it ranked the Vulture Party below the Hyena Party, then it should still do that in the second election. In other words, the overall ranking of these two candidates should just depend on the independent rankings, the relative rankings of these two candidates in particular within each person's set of voting preferences. It shouldn't depend on how we rank the other candidates. We can, if these two stay the same, we can rearrange everyone else as we please. So that's just what I've written here. The relative rankings of the two candidates should only depend on how each voter ranked those two candidates against each other. I should have proofread. Okay, so let's look at some examples and see if we can come up with a system that actually has these properties. I don't know if there's been enough time for anyone to actually do the survey, but I will inform you that the system that I use, that I will use to give us an overall ranking for everyone who responded, will in fact satisfy all of these properties. It's magical. I've got a top secret proprietary algorithm for combining ranked choices into. I see there's 4 responses. I'll go through a couple of these examples and then we can. I'll give you the overall results of what people's favorite quote unquote integer is. The gimmick here is that all of those numbers are all approximately an integer to within at least 5 decimal places for each one. But yeah, so if we only have 2 candidates, this is easy. So let's call them the Leech Party and the Vulture Party. We count how many voters rank the leeches above the vultures and vice versa. And the one with the most votes, the one that was at the top most often, is ranked first. And the other one is ranked second. We just the winner is the one that was ranked first most often. And this does, in fact, satisfy both of our properties. It satisfies unanimity because if every voter prefers the leeches to the vultures, then certainly more voters prefer the leeches to the vultures than vice versa. And so because we picked the one that's got more votes, the leeches have more votes because they have all of the votes, and so they win. So by unanimity, everyone agrees that this guy's better. He will actually be ranked higher. And independence of irrelevant alternatives, while there are only 2 candidates, these are the only 2 that our output could depend on. There isn't any other candidates to muddy the waters. But if we have 2 elections and the relative rankings between the leeches and vultures don't change, then we have essentially the same election. The candidate that's preferred more often also doesn't change because everyone's voted in exactly the same way. So the result shouldn't change. So that's an example that works, but we can, in most election scenarios, we don't only have 2 candidates. So, you obviously can't use a system that's designed for 2 candidates. So let's look at some other aggregation systems that deal with more than 2. So the one that you might come up with if you try to do this yourself is for each candidate, we keep track of an overall score. And every time the candidate is ranked nth, we increase their score by n. So we just add up all of the positions that they were ranked. If they're ranked first, that gives them 1 point. If they're ranked second, that gives them 2 points. Third, 3 points, and so on. So we just add up all their positions across all of the voters. And then we rank them according to who has the lowest total position or lowest average position equivalently, because average is just total divided by the number. And of course, this could result in ties. So we just have to pick some deterministic way to break the ties. So rank the earlier candidate above the later candidate, or break ties alphabetically, or just as long as it doesn't depend on the weather. It only depends on information that's actually fed into the system. So yeah, we rank the candidate from lowest score to highest score, and we find the deterministic way to break ties. And the question is, does this satisfy our properties? So it's fairly intuitive that unanimity is satisfied. If everyone prefers one candidate to another, then they're always ranked higher than the other candidate. So their scores that we're adding together is always lower than the other person's. And so their total score is lower, so they will be ranked higher. So here I've put it in a bit more mathematically. Suppose voter I ranks the hyena party in position HI and the vulture party in position VI, and everyone agrees that the hyenas is better than the vultures. So we have that HI is always less than VI. So when we add all of these together, the sum of all the HI, which is the score for the hyena party, is less than the sum of all the VI, which is the score for the vulture party. And so the system's going to, because the system ranks them by total score, it's going to rank the hyena party above the vulture party. So the question is, does it satisfy the other sort of more contentious criterion, which also seems reasonable at first glance? The answer is, well, I'll spoil the punchline, but the answer is no. Consider these two elections. In the first election, voter 1 gives the list as HVAL, and voter 2 also gives HAVL, and you can see the table there. So I claim that V and L don't satisfy this independence of irrelevant alternatives criterion. So in the first election, V was second, and so had 4 points overall. And L was fourth and first, so they have 5 points overall. So V's got a lower total score than L, so they're going to be ranked above L. Turns out H also has 4 points, but how we break the tie between H and V doesn't matter because 4 is still less than 5. And so V will be ranked above L. Whether it's actually ranked first or second is irrelevant over here. In the second election, though, V was ranked third and fourth, giving them 7 points overall, and L was ranked fourth and first, still was ranked fourth and first, giving them 5 points overall. So V now has a bigger score and now is ranked lower than L. And this violates the independence of irrelevant alternatives criterion, because if you look at each election, in the first election, voter A preferred V to L and still did in the second election. In the first election, in both elections, they ranked L last. And for the other candidate, in both elections, they preferred L to V. So this already shows a drawback in our IIA criterion, is it only considers the positions of these parties. It doesn't consider the other information that we have available here, which is how strongly does the candidate prefer V to L or L to V. So in the first election, the two candidates are sort of indifferent between the two, but has a slight preference for one or the other. But in the second election, voter 1 is sort of indifferent, but voter 2's got a strong preference for L over V. And so maybe it makes sense to rank L higher, even if this doesn't satisfy this IIA criterion that we are interested in. I've just summarized here. The positional voting system that we've just discussed does not satisfy independence of irrelevant alternatives. So maybe another system does. Okay, that was disappointing. I forgot that I put the pictures in between the slides. Okay, this one's called Copeland's method, and what it does, it's essentially sort of goal difference, but for these candidates that we're voting for. It counts how many times they win minus how many, or basically it pairs them off against every other candidate one by one, and it counts how many times it is preferred to the other candidate, and how many times the other candidate is the preferred candidate, and it's the score that assigns the candidate is the victories minus the losses. So it's like runs a whole series of N choose 2 virtual elections between 2 candidates at a time, and says that the person would have voted for candidate 1 if they prefer candidate 1 over candidate 2, and vice versa. Sees who wins, counts victories, subtracts the losses. And so that's the score. So for each candidate, we count how many of the virtual elections they win and how many they lose. And the candidate scores the number of victories minus the number of defeats. And Copeland's method is called a Condorcet method. It's guaranteed to find a Condorcet winner if one exists. So this is a property arrow that's not relevant in Arrow's theorem, but is a property that people are sometimes interested in when discussing voting systems, is whether they are Condorcet methods. So what is a Condorcet winner? It's a candidate that would beat any of the other candidates if we were to hold a head-to-head election between the 2 candidates. And you can sort of see just by the way that Copeland's method is constructed that it will be a Condorcet method, because it's explicitly designed to take these pairwise elections into account and count how many times you're going to win or lose. But this is Also, a reasonable property you might want a system to have is that it finds these Condorcet methods. This candidate sort of preferred more often than every other candidate. So, is Copeland's method unanimous? If everyone prefers A to B, does Copeland's method rank A higher than B? Well, if everyone prefers A to B, then every time B beats a candidate in a sub-election, so does A, because if B was ranked higher than someone, because A ranks higher than B, A is also ranked higher than that other person we're considering. So every time B beats a candidate, so does A. And every time, so that means that the number of sub-elections that A wins is at least as large as the number that B wins. And you can also, I didn't do this point by point properly. But similarly, A has at most as many defeats as B does, because every time A is defeated, B is also defeated. But A wins the sub-election against B, because everyone prefers A to B. So A would win the sub-election against B. So every time B wins, A also wins. Every time A loses, B also loses, but A beats B. And so you can then see, you can do the maths, and you'll see that A's score is going to end up higher than B's, and so Copeland's method is going to rank A higher than B. And so again, now the question is, does this satisfy this other dodgy-ish criteria, the independence of irrelevant alternatives? This example is a bit more complicated, and I'm not going to go through the actual calculations to determine the ranking in each case, but it turns out that with this set of votes from 6 different voters in 2 elections between these 4 candidates, that in the first election A is going to beat D, but in the second election D is going to beat A. And this is problematic because voter 1 preferred A to D in both elections, voter 2 preferred A to D in both elections, voters 3 and 4 preferred D to A in both elections, and voters 5 and 6 preferred D to A in both elections. So as far as D and A are concerned, these are the same elections, yet they ranked differently in these 2 elections. So the conclusion is that Copeland's method also does not satisfy the independent of irrelevant alternatives. And then is everyone happy so far? I assume. I'm going to continue, and you can ask questions a bit later, I suppose. The last method we're going to look at, again, disappointing, sigh, is runoff voting. And here what we do is we count for each candidate how many times they are the most preferred candidate. And the person with the least number of that appears as candidate number 1 the least number of times is then ranked last and eliminated. So essentially it's as if we took everyone's first choice and just had a normal election, like the kind of election you imagine, just with everyone's first choices, and see who wins and loses. And the loser in this election, just between the first choices, is the one that we rank last. And then we eliminate them completely, and we repeat this process. So from the remaining candidates, we see who has got the least number, appears the least number of times as the first choice of whoever's left. They are now ranked second last. They eliminated completely from consideration, and we repeat until we've gone through all of the candidates. So the candidates ranked first the fewest number of times is ranked last and eliminated. Like I said, we count how many times. Just repeating myself if I actually read these out. But like it's essentially we just have a normal election, and whoever would lose is placed last. And then, it turns out that the South African Parliament uses a version of runoff voting to elect the President of the Republic of South Africa. The President, most people don't know, is not actually necessarily the leader of the largest political party. In fact, I don't know if the Constitution even sort of recognizes an official leader of the political parties. And also the president is not elected directly by the people of South Africa. That most of you probably already did know. You vote for a party, not for who you'd like to be president. Whereas in the United States, you sort of it's also indirect. You don't vote directly for the president, but you do give your choice between the candidates explicitly as who you would prefer as the president. But then the Electoral College actually makes the final decision. That's a whole different discussion, and it turns out that the states can allocate the electoral votes however they want and can completely ignore the votes of the people actually living in that state. But in practice, they just cast all of the electoral votes for whoever has the majority in their state. But anyway, but in South Africa, as you know, we elect political parties, not the president. And what most people don't know is that it's not the leader of the largest party that's the president. And in fact, any member of parliament can nominate any other member of parliament to stand for president. And then everyone votes for one of the candidates. And if any of the candidates has more than half of the votes, if they have a majority, then they become the president. Otherwise, the person with the least number of votes is eliminated and everyone votes again. And this carries on until one of the candidates actually does have a majority. So this is a form of runoff voting. We eliminate the least popular candidate the whole time and then have another election. The difference between this version and the one we looked at is that in Parliament, you can change your as a member of parliament, you can change your vote for president between each of the consecutive votes. You're not obliged to keep voting for the same person. Now, in practice, only one round of this kind of voting has ever been necessary because our largest political party has had a majority in parliament, has always nominated its leader as for president, and has always voted for its leader. And so its leader has always had a majority of the votes for president. And so at least, even though it's technically not how the president is elected, in practice it is because our dominant political party does have a majority of the support of the country at large. So the question is, again, are we going to return to these sort of arrow criteria? Is it unanimous? If everyone prefers A to B, then will A be ranked higher than B? Well, if everyone prefers A to B, then A will always be the first remaining choice at least as often as B is. In fact, B is never ranked first as long as A has not been eliminated because everyone prefers A to B. So, once if B can't be ranked first because A has to be ranked higher. And so B is always going to be ranked first fewer times than A is. In fact, because it's never ranked first, B is probably going to be the first person to be eliminated. Again, we have to break ties in some way. It might be the case that there's multiple candidates that are never ranked first. But anyway, the point is that A is going to survive longer than B does. So B will be the least popular candidate before A is, and so B is eliminated before A is. And so B is, by the way we designed this, B is ranked lower than A is. So this, like I said, unanimity is sort of most voting systems most people come up with is going to satisfy this criteria. It's IIA that's the more difficult one. And so consider the following two elections. We've got 5 voters and 3 candidates. And in the first election, we count how many times each candidate appears in first. So A is first twice because voters 1 and 2 ranked A first. C is first twice because 3 and 4 ranked C first. But B is only ranked first once, because only voter 5 prefers B the most. And so B is placed last and eliminated. So then we look at everyone's preferences for the remaining candidates. And among the remaining candidates, A is going to be ranked first by voters 1 and 2 because they still prefer A the most, and by voter 5 because B has already been eliminated. So we ignore 5's vote for B. So there's now 3 votes placing A first, and only 2 vote placing C first. So C is then going to be placed second last and eliminated, and A is going to win overall using the runoff voting system. And in the second election, you can go through a similar sort of thing. You see that C is never ranked first in the second election, so they are placed last. And then once C has been eliminated, B is ranked first 3 times by voters 3, 4, and 5. So B is ranked first and A is ranked second. So the result in the first election with this set of votes is ACB, and in the second election, it's BAC. And this is a problem because everyone who preferred A to B in the first election still does in the second election and vice versa. Voters 1 and 2 preferred A to B in both elections. Voters 3 and 4 preferred B to A in both elections, and voter 5 preferred B to A in both elections. As far as B and A are concerned, these are the same election, yet their relative rankings have been reversed. In the first election, A beat B, but in the second election, A did not beat B. And so runoff voting, or this version of runoff voting, does not satisfy. Runoff voting is usually used to select an overall winner rather than trying to produce a ranking. So it's like the South African Parliament example. If you can't change your votes between rounds, and we do it in the way we did here, then it's usually called instant runoff voting. But here, this is sort of an adaptation of instant runoff voting that will produce a ranking of the candidates rather than a overall. It also produces an overall first candidate. The winner is just the person at the top of the ranking. So runoff voting does not work. Is there anything that does? Well, there are many other methods that exist for the purpose of, or can be adapted for the purpose of, aggregating a set of rankings into a unified one. Like I said, runoff voting is usually used to pick an overall winner, not to create a ranking, but we can adapt it to create a ranking. There's, long lists of voting systems, and you're welcome to do reading. There's the border count, there's ranked pairs, which is horrendously complicated. There's the Kearney-Young method. There's many, many, many more. You might be surprised to hear that none of them satisfy the independent or irrelevant alternatives, and all of them satisfy unanimity. It's trivial to satisfy unanimity, basically impossible to do IIA in a satisfying way. So is there any method that does? Well, I promised you that our survey here, I will aggregate the rankings with a method that does satisfy all of these properties. And so I've got the voting results here, and let's get the overall results. So it has been determined that our favorite natural number or integers in order of preference. The first one is phi over e plus e to the e plus pi squared over e times pi, otherwise known as approximately 3. In second place is e to the pi minus pi, or approximately 20. In third place, we have e minus this horrible expression, but the nice thing about this horrible expression is it uses each of the digits from 1 to 9 exactly once, and approximates e remarkably well. You can you can ask yourself the question of why does it approximate e that well? There is a very good reason. Think of the limit definition for e. So our number 3 is approximately 0. It's e minus something obnoxiously close to e. In fourth place, we have pi to the 9 over e to the 8, which is approximately 1. In fifth place, we have 22 pi to the 4. I've forgotten what that's equal to. It's 2000 and something, but it's also like to 5 decimal places, it's an integer. And in sixth place, we have the horrendously large e to the pi square root of 163. And it's also approximately an integer. So you might think I just made up the rankings. I could have. But I do promise that the method I just used to determine our overall ranking that is in fact deterministic. It is in fact universal. It does in fact satisfy unanimity. If everyone preferred one of these integers to another, it would have been ranked higher. And it does satisfy independence from irrelevant alternatives. What on earth could it be? I should have posted a link to the thing in the chat. So I'll confess, this is what I did. I just went to the second result that was submitted because the first one was mine, and I just read out their preferences. So whoever voted second, you are our winner today. Your choices dictated the entirety of societies. So the way this system works, let's call it a dictatorship or a monarchy, if you want to make it sound more pleasant. We designate one of our voters as our hopefully benevolent dictator, I mean king or queen. And the overall ranking is just whatever they decide it is. So is this unanimity? Or does it exhibit unanimity? Well, if every voter prefers the hyena party to the leech party, then so does the dictator, just by definition. If everyone prefers 3 to 20, then the dictator in our case also preferred 3 to 20 because our dictator is one of everybody. It's one of the people. Not exactly what you want from a dictator. He's just like us. And so because everyone preferred the hyenas to the leeches, so did our dictator. And so our dictatorship would rank the hyena party above the leech party because it just does whatever the dictator does. So you can see it does exhibit unanimity because if everyone agrees on something, the dictator also has that preference. And because we use the dictator's preference, our overall preference is going to also agree that a certain party is better than another one. And does it exhibit independence of irrelevant alternatives? Well, if we have 2 elections and everyone who preferred party 1 to party 2 in the first election still does in the second election and vice versa, then again, the dictator is one of the people. He also will prefer the one party to the other in both elections. If it's the hyena party, then the hyena party is going to be ranked above the leech party in both elections because we just use the dictator's preferences. And conversely, if the dictator preferred the leech party, then he does so in both elections. And so the leech party is ranked higher in both elections. And like magic, you've got a system that exhibits independence from irrelevant alternatives. So dictatorship does satisfy independence of irrelevant alternatives. The question is there a good reason for this? And this brings us to Arrow's theorem. Arrow's theorem says that if we have an election system between 3 or more candidates, because we saw for 2 candidates, majority rule has all of the properties we want. But if you have at least 3 candidates, and it's deterministic, universal, exhibits unanimity, and this horrendous IIA, then it must be a dictatorship. It's the only option. It's the only thing that works. I haven't prepared slides of the proof, but if there's enough time at the end of this, then I'm happy to sketch a proof. We'll just use some kind of writing software. I was hoping my writing tablet would work, but it's not behaving itself today, but we can make it work. If there's enough time and enough people are interested, then I'm happy to do that. But just as you wanted to say something, Lawrence?
We're at 20 minutes to 2 now, so I don't know how long these last 5 slides would take, but I think we ought to have time, depending on how long the proof is.
I can do it in a couple of minutes, and these last slides are sort of will also just take a minute to go through. It's like a general discussion of Arrow's theorem says we can only have a dictatorship if we want IIA. Because the others are basically automatically satisfied. No one's going to come up with something that doesn't satisfy the other 3. So IIA is really the contentious one here. So Arrow's theorem says that if you want that, if you think it's desirable, then it must be a dictatorship. The question is, does this matter in the quote-unquote real world? And firstly, the thing that you might have noticed is that Arrow's theorem only applies to ranked choice voting systems. In the real world, more information may be available. And also, we have some information of how strongly someone prefers one candidate over another. It's not purely the ranking. Well, it depends. You have to then collect that information. There is a sort of generalization of Arrow's theorem that does apply in that case, but I don't know enough about it to talk about it. So unfortunately, that also is fraught with difficulty. And also, you can't have everything you want in life, even from more complicated systems that take more information into account. But this is something to consider. In the real world, we do have more information at our fingertips. We usually have an opportunity to correct our mistakes. We don't just vote once and then that's it forever. So if we realize that we made a mistake in our results, or that we actually don't prefer the outcome that we got, then 5 years from now, at least in principle, you can vote differently. Whether you actually can is a different question, but at least in principle, we have the opportunity to fix the mistakes as we go. So as long as in the long term we tend towards what everyone wants, then that's still fine. You just have to put up with some inefficiencies along the way. An election between yes and no only has 2 candidates, I say sort of sarcastically. So it's like, should we adopt this? And then you can just use majority vote to pick yes or no. And that is going to have both of those properties. Is IIA even a desirable property anyway? Like I said earlier, IIA completely ignores that even though we rank the 2 candidates the same relative to each other, the strength of that preference could change between the 2 elections. And also in the real world, people's preferences for parties are correlated. So at this point, for the example, I am actually going to use real political parties. Someone who votes for the EFF is a lot more likely to vote for the ANC than for the DA, and is a lot more likely to vote for the DA than the Freedom Front Plus. There's a sort of, it's far too reductionistic to claim that there's a political spectrum that tends from left to right, but it's enough that you do have to sort of consider it, that there is this correlation in the way that people vote for certain parties compared to others. And in fact, on the wiki, I can't remember who proved it, but it's I suppose an exercise for you. On the Wikipedia article on Arrow's theorem, it mentions that someone proved that if you are in the system where everyone has, where all of the options sit somewhere on some spectrum, and everyone has got a preferred point on that spectrum, and they just rank everyone according to their preference. Their ranking is how far everyone is from that ideal point. Then then majority rule, the one where you count who has the most votes and they ranked first, and who has the second most votes and they ranked second, and so on. Then that does actually satisfy IIA under the assumption that you have this sort of linear spread of votes where, I sit here on the spectrum, and so anyone that's close to that is ranked highly, and anyone that's further away is ranked lowly. You can prove that does actually, with that assumption on the underlying voter behavior, that IAA is attainable even by a simple voting system. And so in conclusion, thank you for listening. Let's go back to this. This is the best maths lecture you're ever going to see. Okay, so if you focus my video, you'll be able to see what I'm writing. So we've got, in our first election, we're going to consider the case where everyone votes B as their least preferred candidate. So they vote A or C and then B. It doesn't matter which way around A or C is. And then A or C again, and then B, and then so on. And everyone does this, A or C, and then B. And by unanimity, everyone prefers A. And so A is going to be ranked higher than B, because everyone has ranked A higher than B. Everyone agrees that A is better. And we're going to consider a deviation from this setup where everyone thinks B is the worst, and see how our voting system responds. So we're going to then consider the case where voter 1 suddenly ranks B higher, and everyone else still did the same thing, ranks A or C over B, and everyone else ranks A or C over B, and this is going to have some result. We don't know what it is. And if you keep going, so then 2 people rank B higher, A or C, B, A or C, and so on. And you keep going until everyone votes B at the top. A or C, B, A or C, and so on. B, A or C. At this point, everyone agrees that B is better than A. So at this point where everyone prefers B, we have that B is ranked higher than A. So we started off where A is higher than B. We get to a point where B is higher than A. This does eventually occur, so there must be a first time that it occurs. So let's suppose that this is the first time that B is ranked higher than A, and that it's the kth voter that has just switched B to being their most preferred candidate, and everyone after that still prefers A or C to B. And this is the first time that B is above A. This voter A, we're going to call the pivotal voter for B over A. K is pivotal for B over A. B over A. So that makes sense, right? We start off in a situation where everyone prefers A to B, so unanimity says A has to be better than B. We one by one switch B to being at the top. And in the end, everyone thinks B is better than A, so by unanimity, the voting system would have to rank B over A. And so one of these intermediate states also has B over A. We look at the first time this happens. And the claim is that this pivotal voter B, for B over A, dictates our choice, or can force B to be ranked higher than C. So pivotal for B over A. So pivotal for B. I know this is not the ideal way to do sort of writing, but hopefully everyone can sort of see what's going on. Pivotal for B over A can force B to be ranked higher than C. And how do we see this? Well, we consider, again, we're going to consider a series of elections and see how our voting system responds. So initially, we look at the case where everyone from 1 to k minus 1 votes BCA, BCA, and then everyone from k onwards votes ABC, ABC. Now, as far as B and A is concerned, this is the same as the k minus 1 election on the previous page. We're in the situation where k minus 1 people prefer B to A, or the first k minus 1 people prefer B to A, and the others prefer A to B. So we are still in the situation here. Because of independence of irrelevant alternatives, the voting system has to rank A above B, because it's identical to, not identical literally, but as far as A and B are concerned, it's identical to the k minus 1 profile we looked at earlier. And we can also see that everyone agrees that B is better than C. So by unanimity, our voting system has to say that B is better than C. Because here we voted BCA, B bigger than C, and here we voted ABC, so B bigger than C. So we know the outcome of this profile. We know that it's ABC. We now consider what happens if this vote, so voter number K, instead votes BAC. And everyone else is free to switch their preference for B and C. So here we still have B or C and then A, B or C and then A, and so on, B or C and then A. And here, from here on, we also have A and then B or C, A and then B or C, and so on, A and then B or C. So everyone else can choose how they want to rank B or C between each other, arbitrarily, however they want, as long as they keep where A is ranked the same. And so we're going to try to figure out what the result is in this case. And so as far as A and B are concerned, here we are in the pivotal case from the previous page, where the first K people prefer. So yeah, I'm going to write first K prefer B to A, and the rest prefer A to B. A to B. So as far as A and B are concerned, if we ignore C, this is exactly the same election as the pivotal case that we considered earlier, where the first K people prefer B to A, the rest prefer A to B. And so we know that by definition of how we chose K, that this was the first time that B is going to be ranked higher than A. On the other hand, we can also see that this, as far as A and C are concerned, this is identical to the previous case before we switched the votes. Here, everyone, regardless of how they ranked B or C, they still prefer C to A, just like they did over here, where they picked BCA. Yeah, so here they still prefer C to A. And from K onwards, here they ranked A above C. And here, regardless of how they choose between B and C, they're still ranking A above C. And so again, by independence of irrelevant alternatives, these two elections are the same as far as A and C are concerned. And so our voting system has to give the same result between A and C in this case here as it does in this case here after the votes are switched. And so we see that A should be ranked higher than C. And so we again know exactly what the outcome is. But here we see that B is ranked above C, even if everyone other than voter number K voted for C, ranked C higher than B. I said this is completely independent of how everyone ranks B and C. The only person whose vote matters in this case is this pivotal voter. In any other election, where voter K ranks B above C, independence of irrelevant alternative says that that election is identical to this one, or a election of this form, because here everyone's choices of B and C was arbitrary. So you can just pick the one that happens to correspond to the situation you're actually looking at. As long as this guy ranks B over C, IIA tells us that B has to be larger than C. So K votes B over C implies B is ranked higher than C. So this voter here, voter number K, the person that was the first time that B beats A by placing B above A, can dictate what the result is between B and C. And then the only remaining part of the proof is to show that, in fact, all of these pivotal voters are the same person. And so let's denote by P. A over B is the pivotal voter for A over B. So pivotal for A over B. And if you think about going back to how we defined this pivotal voter, we looked at a sequence of elections where initially everyone ranks A above B, and then one by one starts preferring B to A, and we look at the first time that B wins. So clearly, the first time that B wins has to occur before the dictator for B above A places B above A, because we can use the same sort of proof to prove that there is a person that can force B to be above A. So if the person who can force B to be above A places B above A, then B is ranked above A. So the first time that B is ranked above A has to happen before that. It happens then at the latest. It happens at the latest when the dictator places B above A. So the pivotal voter for B above A, or let's go with the notes I have on the other side of me, the pivotal voter for B over C is going to come before or is less than or equal to dictator for B over C. Right, because once the dictator says B is better than C, it's game over. B is better than C. So the first time B is better than C, i.e. our definition of the pivotal voter, has to happen before that. And this previous thing, we showed that a pivotal voter for B over A is a dictator for B over C, can force B to be ranked higher than C. So this dictator for B over C is the same thing as the pivotal voter for B over A. So pivotal voter for B over C is less than or equal to the pivotal voter for B over A. Also, once this dictator says B is better, B is always going to be better. So the first time that C can be let me just think about why this is true. The claim is that the pivotal voter for C over B comes after the dictator for B over C. So because before this, everyone prefers, before the pivotal voter, we're assuming that everyone has switched their vote to C over B. So if the dictator hasn't switched their vote yet, if the dictator's still voting B over C, then because they're the dictator for B over C, not the dictator overall, that's what we're still proving, but because the dictator for B over C prefers B to C, B is still ranked higher as long as this person is ranking B above C. So once we get to the person where them flipping their vote causes C to be ranked above A, we have to have gone past the dictator, because otherwise we'd still be seeing B be above C, because the dictator's still voting B above C. And so that's why the dictator for B over C comes before the pivotal voter for C over B. And then reversing this argument, you'll see that the pivotal voter for C over B is less than or equal to the pivotal voter for C over A is less than or equal to the pivotal voter for B over C. So you have that this guy comes before this one, but also after this one. And so they must in fact be the same person. And so our dictator for B over C is the same as our dictator for C over B, is the same as our dictator for A over B, is the same as our dictator for, you can go through the details and work out that this dictator for this candidate over this candidate is the same in every case as a consequence of this. And so in fact, there's a universal dictator that as long as they rank one candidate above another, that's also the overall result. Sorry about like this setup about trying to hold my camera above a page while I'm writing. It's the hopefully that's reasonably clear, but if you have any questions, you're welcome to ask me, and you can also just send me a message separately and ask for clarification about anything. And yeah, that's my talk.
Great, thank you
for
very much.
listening.
Yeah, I enjoyed it. Enjoyed having you back, and this time I can't recall exactly the politics that were involved last time, but
I can't either. Yeah. I lost the slides from last time, if I'm honest. I think they're on the laptop of mine that was stolen recently.
Okay. Yeah, sorry about that. Yeah, on behalf of everyone then, I just want to say thank you for being available. Again, you're, I think, one of our most consistent speakers. I can say that.
If 2 talks is all that's required to get there, then yeah, everyone else needs to.
No, I appreciate it a lot. So yeah, if anyone has any questions still, let's give a minute for that, and if not, then we'll discontinue.
Okay.
So I'll just have a bit of a chat while people are maybe conjuring up questions. Would you then suggest that voting for the new committee, that it just be left to the chairperson of some, or an external moderator? Or
I suggest that you pick someone completely at random. This has actually been a serious proposal by various people throughout history. It's a voting system called sortition, where we literally just elect our leaders at random. And there's even some, reasons to suspect that this is not as bad as you might think it is, because as long as your sample is chosen sufficiently randomly, you only need like 1,000 people to be representatives of society at large. So pick a random 1,000 people and let them make the decisions. They are parliament, and you've got a 95% confidence that they vote the same way on this issue as the population at large would. Alternatively, just throw all the names in a hat and draw one of the names out of the hat completely at random, or the votes in the hat, rather, not literally the candidates' names. Put all the votes in the hat and pick one at random rather than bothering to count them, because counting votes is tedious and takes too long. And again, this is not as bad as you might imagine, because the probability that someone wins this way is just equal to the proportion of the votes that they got. So
I'm sure if to be a little bit political, if that was the case when the 1994 election was done and the one vote was against.
Yes, there's obviously dangers to this. I wouldn't actually recommend it in reality, but I mean, it does raise an interesting question, because these are not that different to sort of democracy at a fundamental level. It's still like, we aggregate. It's given that 1,000 people are likely to come up with the same decisions as society at large would, if you don't trust 1,000 people to make the decisions, why do you trust society at large to? I mean, there's obviously caveats there that you might happen to just randomly select 1,000 people that are literally Hitler, but
yeah,
it's improbable.
That's a bad sample that you have there.
So let's rather not do that. Let's keep things the way they are. I like proportional representation. I think it's a good approximation to the results that you would have got if everyone was to vote directly, because like the best method is everyone just votes directly on every policy proposal. This just gets tedious, and you've got better things to do with your life than sit around all day, every day voting, which is why we elect representatives to do it for us. Or you could have a mixed model where some issues are put to the popular vote and some are the more mundane, everyday things are left up to the appointed representatives.
Okay.
There are options.
So to be full circle, the answer is still no on our initial question.
I don't think that the society should become a dictatorship. No, I think I have ideological problems of that. But I mean, you're welcome to make a different decision.
No, I think we're fine where we are. So then, yeah, it seems no one else is posing questions and we're just having a casual chat. I'll thank you on that note for the presentation, and I hope you and everyone that attended has a good almost weekend. So have a good weekend and a good day.
Awesome.